property does the matrix I minus M share with the matrix M? What property does the matrix I minus M share with the matrix M? When we were talking about M, we said it was a special kind of matrix, right? What kind of matrix is M? What special property M? Jose? Right. The matrix I minus M post-multiplied or pre-multiplied by itself will be in fact I minus M. We just move that a little bit of principal paper, a little bit of multiplying things out.
Did you say that I minus M is equal
It's
to...
I M power. I minus M times I minus M is I minus M. We just showed a few minutes ago that M times M is just equal to M, the M that we had there. And we could also, if we wanted to slog through the algebra, we could show that the matrix I minus M is also idempotent, but that's some algebra that you could do on your own time. What is a quadratic form?
Quadratic form, talking about matrices, or
Any way you want to tell me.
Quadratic form would be when you have some sort of expression that the largest power used in the expression needs the same power.
Okay. And you saw quadratic forms for the first time, I believe, in about 7th or 8th grade. And when you plotted them in Mr. McGillicuddy's math class in 7th or 8th grade, and you were first introduced to quadratic forms, what shape did those quadratic forms have?
Parabola.
They were parabolas, right? So now we're going to be a little bit more sophisticated, because we could have parabolas in a multi-dimensional space. We don't have to limit ourselves to just dimensions. It could be any number. So a quadratic form is anything that we could write as in that fashion, Q for quadratic. And when we expand the quadratic, what we end up with is the double sum over the I and over the J of A, I, J, X, I times X, J. And incidentally, if A is, say, T by T, then X transpose is 1 by T, and X is T by 1. So if the subscripts match, of course, you get an X squared. And if the subscripts don't match, you get Xi times Xj. So we can accommodate all kinds of things. Suppose that when the subscripts don't match, the Aij are 0. Then that gives us the equation of a geometric quadratic. When the Ij don't match, then the Aij are 0. So Aii is a number. Oh, in fact, let's make it more interesting than that. Let's say that the Aii are always 2, and the Aij are 0. If you plotted that, what would it look like? Well, we just said that the Aii are 2, I believe. So we're saying that A is, and we'll do a simple example. So that's what I picked for A. So what's the, if that's A, what's the dimension of X? 2 by 1. You got to give me both numbers. Tell me how many rows and how many columns. So that Q is equal to?
1 by 1.
Q is a scalar, right? So when I expand Q according to the rule that I wrote over there, what do I get?
2x1 plus 2x2.
2x1 plus 2x2, but you need to miss a piece here. There's a row here and a column there. You're almost there.
2x1 squared plus 2x2 squared.
And what does that look like in the x1, x2 plane?
Is it a circle?
Yeah, a circle. Suppose that I did that instead. What would it look like? So Mr. Swartwood was right. It was a circle before, and now I changed one of the diagonal terms so they don't all match. And it becomes what shape does that figure have? An ellipse. Okay, so it's an ellipse. Or what's its orientation? We always talk about a principal and a minor axis in ellipse. So one of the long axis lines up on one of the long axis lines up on one of the basis vectors, either x1 or x2. Suppose I did that. Now what shape does it have? Just one more. You want to tell me again? What shape does that have? Still an ellipse, but something happened to it. If I tilted off the coordinates, the ellipse or the oval has an orientation that's neither horizontal nor vertical. It's oriented somewhere in between. Why is this important? Why is this important? Why am I bringing this up? Did you have undergraduate econometrics? You never talked about regression analysis? Do you remember ever hearing about heteroscedasticity? You know what a normal distribution is, right? Like we might say something absurd like SAT scores are normally distributed. Immediately what pops into your mind is that SAT scores density function is a nice symmetric bell shape. And we might even say something like the math SAT score has a normal distribution, and the verbal SAT score has a normal distribution. And beyond that, they have a bivariate distribution. And so you know that in the math plane, density function is a nice symmetric bell shape group. In the verbal score plane, there's a nice symmetric distribution. So when you put the two together, verbal score along one axis and math score along another axis, and the density of the first density is the vertical tension, what it looks like is the Liberty Bell. Right? This is three-dimensional. And so you get the Liberty Bell. Well, when you project the Liberty Bell down onto the floor, like a topographic map, you get nice symmetric circles, rings that represent the different altitudes of the different segments of the Liberty Bell. But suppose it's the case that the variance of math scores is different than the variance of verbal scores. Well, now what you've done is take that Liberty Bell and you squashed it a little bit. So that now when you cut slices through it, you get ellipses or ovals instead. When you project them down, you get ellipses on the floor. Or, if it's the case that kids who do well on the math part often do well on the verbal part, but the variance is different between the two tests, then you squash the Liberty Bell a little bit out of ground, and you turned it a little bit. So now when you project the topographic map down onto the floor, you get ellipses that are a little bit off the axis. So you can deal with very sophisticated errors by thinking of things in that way, or turning to a random variance. Since you didn't have econometrics before as an undergraduate or not enough statistics,